Good evening, everyone. As principal of Massey College, which is a co-sponsor of tonight's fourth CIFAR Massey lecture, it's my honor to offer one of the welcomes you will receive tonight. In doing so, I note with respect the ancestral lands that the Bader Theatre and Massey College occupy. These are lands that were originally the lands of the Huron-Wendat, Seneca, Ojibwe, and Haudenosaunee. The most recent First Nation to own this land were the Mississaugas of the New Credit River, whose chief, Chief Stacey Laforme, is an elected honorary senior fellow at Massey, along with His Royal Highness Prince Philip and Sir Christopher Patten, Chancellor of Oxford University. And germane to tonight's subject matter, I would point out that the Anishinaabe have their own tradition with respect to sky gazing. They had a group in their First Nation known as the Stargazers, referred to in the Anishinaabe language as the Wabino Inin, or the Morning Star Man. And these were the people who were privileged to have a full knowledge of the sky world as available in those days. And these are the people who worked very hard to associate day-to-day life with their understanding of the sky as they could observe it in their time and place. Welcome to the CIFAR Massey Talk on Science and Society. For the past 4 years, Massey College and CIFAR have been working together to bring these science talks to the public. These talks are intended to explore the connection between research, broader society, and help catalyze new ways of thinking. Each year, we invite a very distinguished scholar, speaker, to discuss an interesting and important area of their research. Tonight, we will hear from CIFAR Senior Fellow Victoria Kaspi, who will be more properly introduced in a moment. And she will speak about mysterious cosmic phenomena called fast radio bursts, and about how researchers are working to understand them. In the process, we will learn a great deal about how modern astronomy is done, about the nature of our universe, and about a new Canadian telescope that could provide novel insights into a number of important questions. The sky, ever since the days of the First Nations, has been the object of awe and study and understanding, and a wondrous mix of observational science, new technology, and a genuine appreciation of the larger universe of which we are a part. Of course, the Canadian Institute for Advanced Research is itself not only an interdisciplinary platform for leading-edge research on so many vital areas of society, but a true generator of intellectual capital. And when you think about that, there are few Canadians who have done more to generate new science in a way that, on the HIV issue, literally saved thousands of lives, opened up new doors, and shone a great and broad light in the darkest and most threatening of environments. I'm delighted to introduce my co-host this evening, the President, CEO of CIFAR, Dr. Alan Bernstein, President of CIFAR, but most importantly, a Senior Fellow of Massey College. Alan.
Thank you very much. I am delighted to be here, both as you just heard from Principal Siegel, as the President of CIFAR, and as a Senior Fellow from Massey, and I'm really honored to be having both those roles. And I'm really very much looking forward to introducing our fourth Massey CIFAR lecturer, Dr. Vicki Kaspi. For those of you who are familiar with CIFAR, who are not familiar with CIFAR, we are Canada's Global Research Institute. We were founded 38 years ago, roughly, on two disarmingly really simple ideas. The first is that research is essential to improve the human condition, and I would add probably more so now than ever. And second, the best way to do research and to address the really complex, difficult questions that the planet faces today is to bring the very best minds together. Today, CIFAR has close to 400 fellows, advisors, and scholars who come from 120 institutions and 22 countries, addressing questions ranging from understanding the genetic networks that underlie our health and disease, to the launch of the revolution in artificial intelligence, to gravity and the extreme universe, which you'll hear a lot more from our speaker this evening. I believe that CIFAR gives our fellows something that is so precious today, which is time to think together, to come across boundaries of both discipline and country to really address interesting and important questions. Since 1982, there have been 19 Nobel laureates who have been associated with CIFAR, including, we've added one this week, most recently, Paul Romer, who was a CIFAR fellow in our program on economic growth in the 1990s, who won on Monday, shared the Nobel Prize in Economics with a colleague. And actually, it's relevant to today's talk because what Paul won his Nobel Prize for was the, I think, disarmingly simple idea that ideas and innovation are what drive economic growth in our economy. And he proved that mathematically and statistically and brought really robust evidence to the fore, something that certainly as a scientist, I almost, it's the air I breathe. So now I'd like to introduce another first-rate mind, not yet a Nobel Prize winner, but, time's on our side. This evening's speaker, Victoria Kaspi. Vicki is a CIFAR Senior Fellow, and she directs our program in Gravity in the Extreme Universe. She's a professor of physics at McGill University, holds the Loren Trottier Chair in Astrophysics and Cosmology, and directs the McGill Institute of Space Science. Vicki's research focuses, amongst other things, on neutron stars, which are massive, dense celestial objects that emit bursts of radiation as they rotate, and that are formed when a massive star explodes. She uses the largest and most powerful radio and X-ray telescopes in the world to study their physical behavior. She also uses a new telescope, a made in Canada telescope called Chime, which I'm sure she will tell us a lot more about in her talk. Her work is shedding light on the nature of matter under really extraordinary circumstances, under these intense pressures and densities, as well as in less extreme settings right here on Earth. Vicki is the winner of many awards and honors, deservedly, including the Gerhard Hertzberg Canada Gold Medal, the Killam Prize, the Peter Martin Award of the Canadian Astronomical Society, and she is a companion of the Order of Canada. Please join me in welcoming Victoria Kaspi.
Thank you very much for that lovely introduction. It's a great honor to be here. I'm very excited to tell you about some of the research that I'm doing right now. It's in the field of astronomy, and as I described to you the phenomenon that we're trying to understand, it's a big puzzle. It's a major mystery right now. I'm hoping also to share with you a little bit about the process of doing research, what it's like to be trying to answer these kind of questions, the twists and turns, and as you'll see, lots of surprises along the way, a lot of unexpected things. Now, when I try and explain to people, what do we mean by fast radio bursts? Here's a sort of arty kind of cartoon of the sort of thing I want you to have in your mind, something all over the sky that's flashing in unexpected places very briefly and then disappears. And I'll explain a little bit more what this phenomenon really looks like, but that's just to get you sort of an intuition for the challenge that we face, because we want to understand a phenomenon where we don't know when the next one is going to be or where the next one's going to be. And so it has gotten quite a bit of attention, this problem. Here it was on the cover of Nature magazine. But another thread that you'll see in the talk is that it's gotten quite a bit of press. In some ways that's wonderful. In some ways, as you'll understand, it's a little strange. Here are some examples. New York Times, LA Times. We've been all over the press. People find this phenomenon really, really fascinating. Now, we say fast radio bursts, and when I say radio, people, or at least people of a certain generation, picture this device, something that detects invisible waves with an antenna. and which has a dial on it where you can change the frequency that that antenna is sensitive to, or at least that is amplified enough that you can hear it through the speaker with your ears. So there's a dial here, and there's FM, which is telling you in megahertz, which has to do with the number of oscillations per second of the radio wave that you're interested in. The frequency of radio waves is going to play a very big role in this talk, and so I wanted to introduce it using a device that you're all familiar with. But of course, when we say radio, these waves that are invisible that you can't see are a form of light. The electromagnetic spectrum is the full wavelength or frequency, depending on how you want to look at it, of electromagnetic waves, of which the light that you're using to see me right now is a small part. That's the visible portion of the spectrum. But radio is just another part of the electromagnetic spectrum. It is a much lower frequency, longer wavelength kind of light, but it's light all the same. And nature produces all sorts of different light. When you look up at the sky, you're seeing the visible portion because that's what your eyes can see. But if you had antennas for eyes, the sky would look vastly different. And you might notice things flashing off and on all the time. And that's called the phenomenon of fast radio bursts. So what does this phenomenon consist of? Brief bursts of radio waves, as I said, and now I'm going to quantify brief. They last only a few thousandths of a second. That's a few milliseconds. There's a range. There's all sorts of things you can measure here, and we've measured, and some of them are even less than a thousandth of a second, sometimes tens of millionths of a second. Something very brief. The first one of these events was detected or reported in 2007 by a group using the Parkes radio telescope. This is what the Parkes radio telescope looks like. It's you can just for scale here. I'll use this. This is a 64-meter aperture. This is a 3-story building down here. I actually did my PhD in there. It's a lot of fun to work there with the giant telescope on top of you. And as you can see, the radio waves come in and are focused to a focus cabin where there's antennas that are then, the signal is amplified, digitized, and read down into computers in the building downstairs. So since 2007, we've detected about, so this slide is actually a few hours out of date. So we've detected, as of yesterday, it was about 30 of these fast radio bursts had been detected, and today it was just a Nature paper announcing the detection of 20 more. So today, so about 50 of them have been detected since 2007, but we know that the phenomenon is actually much more common. We can estimate that the all-sky rate, that is, if you could look at the entire sky all the time, these things are happening about 1,000 times per sky per day. So if you could look everywhere and add it all up in 24 hours, you'd see about 1,000 of them. So it's something that's ubiquitous in the universe. This isn't uncommon. And we had no idea this existed before 2007. You could ask, why did you find it then? It has totally coupled with the power of computers, computing power, ability to record data, digitize data very fast, and then analyze it also. And we have and the bottom line is we don't know where they're coming from. So something ubiquitous in the universe of totally unknown origin. We don't know what they are. One thing we know is they're not microwave ovens. And that you may say, what is she talking about? You'll understand shortly what I mean by that. Now, what do they look like? So this was sort of a press photo that was created. This is not what they look like. You can't see radio waves. But this is sort of to give you an idea. Something goes burst and hits the telescope. But that's not what they look like. This is what they really look like to us, to astronomers. We take the digitized signal from the radio telescope and we put it into computers, and we're now showing you a digital version of what we actually see. And so just look at this inset for a moment. Time is going on this axis, and basically there's nothing but noise coming from the radio telescope initially, and then there's the burst. The burst happens, it gets really bright, and then it goes away and it does not come back. So that's the burst. But that's actually a simplified version of what we see. In fact, the radio telescope, the antenna that's on the radio telescope in the focus there is sensitive to a wide range of radio frequencies. And if you look at all the different radio frequencies that it's sensitive to, that's what this bigger plot is. Time is still on this axis, so time is moving along here. And on this axis is radio frequency, just like the dial on that radio I showed you, except we can see all these different frequencies at once. And on that radio, you can only listen to, roughly speaking, one at a time. Here, we can listen, if you want, to a whole range of frequencies, not megahertz, gigahertz in this case. But what happens is the signal does not arrive at all the radio frequencies at the same time. And this is a phenomenon called dispersion, and I'm going to spend a little bit of time on it because it's absolutely crucial to this talk. I really want everybody to understand that the signal arrives earliest at the highest radio frequencies, and it sweeps through the band as you look, you're sensitive to all these frequencies, but it comes in at the highest radio frequencies first, and it's delayed at the lowest radio, at the lower radio frequencies. And you probably, your eyes are drawn to this stripe here. That's some TV station or something or a radio station that's at a fixed radio frequency. That's a nuisance to us. We know that's terrestrial. This signal, by virtue of the fact that it sweeps in and arrives at different times at different radio frequencies, that's the crucial piece of information. This dispersion phenomenon, I'm going to explain a little bit in more detail, is what's telling us that these events are coming from far, far outside the Milky Way galaxy. They're coming, in fact, what we infer from that, just that sweep right there, is that they're probably coming from the furthest reaches of the universe, from what we call cosmological distances, distances that are appreciable fractions of the ages of the universe away. That's Dunk Lorimer. He led the team that found the first one of these. Now, when I say that the events are coming from far, far outside our galaxy and from cosmological distances, I want to be sure we all understand what that means. So let's talk for a moment about the scale of the universe. You're probably familiar with this artist's rendition of the solar system. There's the sun, there's the planets. It's a terrible one. They don't travel on rings. They're not, this is totally not to scale. There's really a big gap between Mars and Jupiter, asteroid belt, and we're not that close. You got to hate scientists sometimes to take a beautiful picture and just tear it to shreds. But anyway, you get the picture. This is the solar system. You're familiar with that. But the solar system, that whole thing is just a tiny dot in a spiral galaxy called the Milky Way. This is not the Milky Way. You can, of course, be sure of that fact because you cannot take a photo of the outside of your home when you're standing inside of it. It's not possible. This is probably a lot like the Milky Way if you could zoom out and look back. And this red dot, which is probably something like 1 million to 1 billion times greater than the size of the solar system. Just to be clear, I had to make it this big so you could see it. The solar system is a speck on this scale. Is at the outer reach of this Milky Way galaxy. And by the way, just to show some pretty pictures, we're in the galaxy, we're in the disk of the galaxy, and so the Milky Way doesn't look like a spiral to us, but you can see it viewed edge on because we're inside of it there. But just to make clear the scale of the universe, here's the Earth, here's the scale of the solar system. You can't quite see it, but if you can see, I don't know if you can turn the lights down a little bit here, but the red dot is always the previous scale in this image. So here's the scale of the solar system with the sun in the middle. I don't know if you could see. And this is now, if you zoom out by factors of many, many thousands to millions, this is the interstellar local neighborhood, local area, region, the closest stars, of which the sun is just one roughly there in the center. And now zooming out by, again, a similar factor, an enormous factor, you're now at the scale of the Milky Way, where that entire interstellar neighborhood is on the outer regions of the Milky Way galaxy. And then if you zoom out, actually this time not a huge factor, about a factor of 10 to 100, there's the entire Milky Way galaxy in the local galactic group. Galaxies like to be in groups, and so this is a group of galaxies. The Andromeda Galaxy is another big galaxy in our local group. And if you zoom way out of that also, the whole local group of galaxies is just a dot in the Virgo supercluster of galaxies. So galaxy clusters like to cluster. And then if you zoom out of that again, this entire supercluster of groups of galaxies is a tiny smudge in a local supercluster of galaxies. And then if you zoom way out of that, you get to the observable universe on the largest scales, which is homogeneous and isotropic. Looks the same in all directions. It's now a remnant of this primordial soup that formed it billions of years ago. And this is the scale, this is the distance scale in which we believe fast radio bursts are arriving. The largest scales in the universe, that's where they're coming from. And we could tell all of that from that dispersive sweep. So let me explain this. That's quite a claim. Okay, I got to unpack that. That's huge. So how can we be so sure? So let me just talk briefly about dispersion of light. So you're actually all familiar with dispersion of optical light, the light that you can see, because when you pass white light through a prism, you know that the prism splits geometrically the different colors. The white is actually made up of all those colors together, and the prism splits them. And that's also the cause of the rainbow. Water droplets in the air will split, disperse white light from the sun. But what you might not realize is that in addition to the geometric dispersion, there's also a time dispersion, and that if you could pulse the prism, you would see that the colors arrive in slightly different times. Different colors travel at different speeds in a medium, like glass or water. Now, you might have thought, wait a minute, E equals mc squared, where c is the speed of light. That's a constant of nature. And that's actually true in a vacuum. So as long as that light's traveling in a vacuum, then the speed of light is constant and the same for all colors of light. And that's all across the full electromagnetic spectrum. Optical, radio, gamma ray, everything, C. But in a medium that is not in a vacuum, the speeds are different. And space is not a vacuum. So here's some cute little geeky jokes. Interstellar space is not a vacuum. It is filled with all sorts of there's dust, there's neutral atoms, there's ionized atoms. In particular, there's free electrons. There are free electrons throughout the galaxy. I'm going to show you a nice map of them shortly. And it's those free electrons that disperse radio waves. So the prism, in the analogy between the dispersion of white light into the colors of the rainbow, the free electrons in our galaxy act as a prism for radio waves. I'm about to show you a contour plot. Now, we're be sure we're all on the same page what a contour plot is. You see contour plots if you look at maps where the lines are lines of constant altitude. So you can see, a mountain here, and each line is has a label on it for the altitude. And if you walk on that line, the altitude is constant. So that we can do the same thing in the galaxy with free electrons. So we know we have mapped out using galactic sources, in particular the neutron stars that I love to study. Here's another spiral galaxy, not the Milky Way. You know that. This is actually a representation of the Milky Way galaxy, where the darker color indicates greater density of free electrons. So we have mapped this out. And this is a contour plot showing you the same thing, where here we are in the outskirts. That's that dot there, and the center of the galaxy is where this little cross is. And these lines are, roughly speaking, where our spiral arms are. And these are contours of constant total number in some arcane units. Don't worry about it, what it is. The total number of electrons in that direction. So if you see some galactic source from a certain direction, you can measure the sweep of its radio waves and then look at the map, and it tells you roughly how far away it is. So we use these kind of maps to measure from sweeps of galactic radio sources that burst distances. So we know something happened at a certain distance. There's a certain sweep in how radio waves arrive. That tells us the distance, roughly speaking, to the source. And in particular, from our knowledge of the distribution of electrons in the galaxy from galactic sources, we know what the maximum is in any direction. So we know, roughly speaking, from the map, and it's a three-dimensional map, you go in any direction, we know how many free electrons total there are in our galaxy. It's quite well known. And so this is how we determine distances. So just here's your little cartoon. The fast radio burst source goes off. It emits all radio frequencies at the same time, but as they travel through free electrons in interstellar and intergalactic space, they get delayed because of dispersion and spread out. And so, that's this, if this is, again, radio frequency and time, it, just like a prism, spreads out the light in time. Different color radio waves, they travel at different speeds in the plasma made of free electrons. They act as a prism, and it washes out any short burst of radio waves. It spreads it out over time, so that if you just added up all the radio frequencies, you would see a totally smeared out pulse. We have to correct for this effect, and the degree by which we correct is telling us the distance. Okay, so I hope you were all able to, but it's a little bit complicated. If I lost some of you, just understand this. From the amount of sweep here, we measure this sweep. The total maximum in the direction this event came from, in those arcane units of Mach contour plot, was about 25. We know the galaxy can only account for a much smaller sweep. The sweep we saw was over 10 times, almost 20 times, the maximum sweep our galaxy can possibly produce. This is what's telling us it can't come from our galaxy. The models of the free electrons that we've built from years and years of observations of galactic sources tell us this thing has to be way outside our galaxy. And by way outside our galaxy, I mean it has to be at a cosmological distance, because the sweep is so large, and intergalactic space is even more closer to a vacuum than our interstellar space inside the galaxy. This thing has to be coming from a cosmological distance. And if it's coming from a cosmological distance, if it's that far away, then intrinsically it must have been very, very bright. So, this phenomenon is kind of frightening. This is something ubiquitous, 1,000 times per sky per day. We don't know what's causing it, but it's for cosmological distance visible here on Earth. Something extremely bright. Now, at the same time this was discovered at Parkes, they started seeing quite a few of them, but some of them had a slightly different behavior, especially that sweep, that telltale sweep. They had kind of strange frequency sweeps. This is one example of a type of fast radio burst. They called them peritons. I'm not sure why they call them that, but just to distinguish them from the bulk of them, which looked much more like the standard sweep that I've shown you in the Lorimer burst. This one, it's sort of clumpy, and it's sort of broader in certain frequencies than others. And there were some other anomalous things about that I don't have time to get into. So they tried, why are these a little different from the others? They didn't really understand until they made a plot of when they arrived by time of day. And so this is a plot showing the gray ones, the light gray ones are all the peritons, and this is time of day in Australian local time. And the dark gray ones are the normal sweeps. And they noticed that the peritons, the weird sweep ones, they tended to occur most often at lunchtime. And so this was a clue that, how could the universe know when lunchtime is at local time at the Parkes telescope? That could not be. And what they realized very quickly once they saw this plot, was that it had to be something local. And it turned out, so the Parkes telescope, if you actually go there, there's a long road here, and at the end of the road, there's the visitors building where the astronomers can sleep and get something to eat. And it turned out that a periton is created when the microwave oven is operating and someone opens it prematurely. So it wasn't just microwave oven had to be on. No, somebody had to be impatient. And the telescope had to be oriented roughly in that direction. And if they opened it when the telescope was roughly oriented in that direction, you got a periton. And there was a grad student who sorted all this out. And, had a stop, had a clock, and was note-taking, open, close, right? Open, close. And they looked and they saw exactly peritons. They could then predict it, and they knew that the weird sweep ones, those were not astrophysical. And I love telling this story because I'm so proud to be a scientist. This is one of the most prestigious journals in astrophysics, the monthly notices of the Royal Astronomical Society, identifying the source of peritons at the Parkes radio telescope. And look what they wrote in their paper. Subsequent tests revealed that a periton can be generated when a microwave oven door is opened prematurely and the telescope is at an appropriate relative angle. And this is science. It's not just amazing that they figured it out, but they report it in a prestigious journal. And I think importantly, what it demonstrated is that the dark gray ones in that plot, the ones that had the more natural looking sweep, or at least the sweep that's very consistent with interstellar dispersion by a plasma, those did not come at any special time. Those had to be astrophysical, and so they comment on that also. This and other distinct observational differences show that fast radio bursts are excellent candidates for genuine extragalactic events. And we now have seen the FRB phenomenon at many different telescopes, not just those with microwave ovens, so we know they're real. And so what are these things? You're all wondering, I'm wondering, we don't know. Currently, there are more theories, that's even with today's announcement, there are more theories than there are actual events that have been detected, which is a very strange place to be in. But the number of theories, I just listed a few, exploding stars, something exploding, colliding stars, colliding neutron star black hole. There's a paper on comets and asteroids impacting neutron stars, black holes evaporating, primordial cosmic string oscillations, all sorts of ideas out there. But the bottom line is we don't know the answer. But let me tell you about a major clue that we got from a fast radio burst that was detected at this observatory, which is the Arecibo Observatory in Puerto Rico. This is now a much larger telescope than Parkes. This is 300 meters across, so that's 5 football fields. This structure here is a large visitor center, a beautiful museum where many schools in Puerto Rico bring their kids to learn about astronomy. There's a car parking lot down there just to set the scale. This is, by the way, a catwalk. You can walk on this, and there we are. Me and a couple friends are at the top of the catwalk. And if you zoom in, my knuckles are white because it's really scary up there. I don't know why we bother wearing hard hats. They make us wear them, but I don't know. And of course, this was featured in a famous film, James Bond, GoldenEye. And if you've never seen this, it's great just to see the Arecibo Observatory. It's a really, they incorrectly put it in Cuba in the movie. It's not, it's in Puerto Rico. But here's the fast radio burst that we detected at Arecibo. And you can see the telltale, the sweep there, the dispersive sweep. We could correct for this and make it vertical by exactly removing the dispersion, but here we haven't, and you see the sweep. It actually tends to fade away at the lower radio frequencies, which is curious. This is the burst when you sum up over all the radio frequencies. And this was, for a long time, the only burst detected by Arecibo, and it was actually the first one detected at a telescope that was not the Parkes telescope. So the Parkes people were really relieved when we found it because they were terrified there was something else going on at their telescope that they hadn't identified. But then we saw one, so they said, phew. Then we decided that we should be, even though Parkes had been looking at all the fast radio bursts they detected and never seen anything else from those positions. Like, it was a one-off event. We sat on this one, and we watched this position for many, many months, and also we didn't see anything until one day. We went back to that spot, and we saw 10 more bursts from the same source. And this was a big shock. We were not at all expecting this. Now, in this plot, we've taken out the dispersion, just corrected for it, delayed the lower frequencies so that they line up vertically. And you can see all of the different bursts from this source. Some are incredibly bright, some are incredibly weak. Some are very bright across all radio frequencies. Some are only in the bottom part of the frequency band. This was an amazing shock to us, and it was actually found by then graduate student Paul Schultz at McGill University, who we were all shocked. It repeats. Oh, it repeats, and it got tons of press. Everybody was really excited. I'm not sure why. I have a theory why we get so much press about these things, and I'll share it with you shortly. But once you have one that repeats, well, that's big. Because, you would really like to know, or are these things coming from a galaxy? And with the Parkes events, you can't know that. And the problem is that if you look at the sky, that's how well Parkes can find the position of any event that they detect. Okay, every telescope has some angular resolution, that is some limitation on how well they can pinpoint the source of the event. And at Parkes, that region is very large, so that there's thousands of galaxies there that it could have come from. You can't know. And even Arecibo actually can pinpoint things a little bit better, but still there's hundreds of galaxies in the error region of the Arecibo telescope. It doesn't help you. What you really want is a different kind of radio telescope called an interferometer that can pinpoint things really well, the very large array, and we're about to go there in New Mexico. But the problem is that its field of view is so small. So if you only detect an event once, or in other words, Parkes is really good at finding them because it sees a large area of the sky at once, but it can't pinpoint. Anything that can pinpoint can't detect them because they're looking at too small a fraction of the sky and the things are bursting elsewhere. But once you have one that repeats, you can go with an interferometer like the Very Large Array in New Mexico. This is an array of 25, well, in this case, or I forget, we could count, but it's this number of 85-foot telescopes. And you can just stare and wait. And that's exactly what we did. We said, hey, there's something that repeats. If you just wait and you look over there, because it pinpoints so well, we're going to know where it's coming from, and then we can look and see if there's a galaxy. And we looked and looked for months, and nothing happened. The source did not cooperate. We had seen it repeat at Arecibo, so we knew it did. And eventually, they were getting pretty sick of us at that telescope, but eventually it burst, and there was a big boom, and this was incredibly exciting. And right away, the analysis, the Arecibo error regions where we didn't know where it was, these were two different positions that we knew it had to be in this overlap region, and boom, there it was on a map made with the Very Large Array. And this is the Very Large Array data shown in the same way that we showed the Arecibo data before, exactly the same sweep, the same amount of dispersion, and within the error region had to be the source. And once we had that position, so this is how it worked. We had that. Let's go. So then we write to the Gemini Telescope, this large 8-meter telescope on the summit of a mountain in Hawaii, and we say, okay, we know the position. Can we have some time? And they gave us some time. And here came the next shock. So we actually got 9 bursts with the VLA, so we got a precise sky position, and we went to the Gemini Telescope and looked, and this is what we saw optically, like this tiny little smudge. We were expecting a nice big galaxy. And it was this tiny little smudge of a galaxy. It turns out it was incredibly faint. We really needed a large 8-meter telescope to detect that the fast radio burst was coming from a dwarf galaxy. So it turns out there's many different types of galaxies, and they're not all giant, beautiful spiral galaxies like the Milky Way. There's all these smaller galaxies, and this huge radio burst was coming. It was a total shock. We had no idea from a dwarf galaxy. But the good thing was that even though it was a tiny galaxy, we could still measure an independent distance, because it's possible to do that with galaxies. There's a nice way for those of you who know, using spectroscopy, you can measure the redshift, and we measured it, and we knew we had measured it was really at a cosmological distance. So all that business of the dispersion and estimating from the free electrons, you could have questioned, maybe you don't know what you're doing, but in fact, it exactly agreed with what we predicted from the dispersion. So we knew it's definitely at a cosmological distance. There was a McGill postdoc, Sriharsh Tendulkar, who did this wonderful optical work. And then we got so much press this way. Another press machine went out, and even Fox News, that was really exciting. Fox News, surprise! Monster burst of radio waves arose in tiny galaxy, and all this press. Let me. I said I would say why I think we get so much press. So for example, okay, here's the New York Times. A famous science writer, Dennis Overby, did a large article about it. Radio burst traced a faraway galaxy, but caller is probably ordinary physics. I wasn't so thrilled with that. I really liked to visit his home late at night and set off a fast radio burst and see how ordinary he finds it. But meanwhile, the New York Post, scientists say radio signals could be coming from aliens. Like, where did they get that? And we never said that. But I do think a lot of the press that we get has to do with us using terms like radio signals, which might suggest to some people that this is not a natural phenomenon. That was never our intention to suggest anything like that. We are very confident this is a natural phenomenon. It has nothing to do with any intelligent, life forms. But we get a lot of press out of it. So, in any case, I don't think they're aliens. I just want to be crystal clear about that. So FRBs, where do we stand? So at least one FRB repeats. And so far, none other has been seen to repeat. So Arecibo 1 is still unique. Obviously, neutron stars can't collide over and over and over again. Okay? So immediately that source ruled out a whole class of models. Anything cataclysmic, anything where the source of the event destroys itself in the process, well, that's out, at least for that one source. And we have confirmed for that source that they're indeed cosmological, as we had inferred indirectly from the dispersion. But the open questions, do they all repeat? Do some just repeat more often than others? We don't know. What is the bursting source? What keeps repeating? We don't know. And why is it in a tiny little galaxy? You might have thought something that bright would be in a larger galaxy. So, basically, there's all these puzzles, lots of unanswered questions still. We need to find more of these. And that's where this new telescope, the Chime telescope that we've built near Penticton, British Columbia, comes into the picture. So this is, when I say telescope, that's probably not what you would picture. This is an unusual design for a telescope, and I'm going to explain shortly why it's so fantastic. And it is, in fact, the world's most powerful fast radio burst detector today. It consists of 4 cylinders, cylindrical reflectors. So it's a very different geometry from the standard circular dish aperture that I've shown you in Parkes and Arecibo, which are the standard kinds of radio telescopes. This is 4 cylinders, each of which is 20 meters by 100 meters. So the total area here, so I told you Arecibo and football fields. This is in Canada, so it's about 5 hockey rinks in total area. And basically, on the axis of each of these cylinders are hanging 256 radio antennas that are sensitive in the frequency range 400 to 800 megahertz. And that means each antenna actually has 2 different signals, so that's a total of 1,024 antennas times 2 polarizations, for those of you who know. That's 2,048 input signals that all are going into what we call basically a massive supercomputer that is on site. The total input data rate after digitizing these signals going into the supercomputer is 13 terabits per second, which is comparable to the entire cellular network in the world. So we have basically the cellular network in the world all being reduced in real time as part of this telescope. And this is a collaboration The lead institutions, McGill, University of Toronto, UBC, and National Research Council, the Dominion Radio Astrophysical Observatory in Penticton, and we also have collaborators at Perimeter, the U.S. National Radio Astronomical Observatory, West Virginia University, MIT, Yale, and Carnegie Mellon. Here in University of Toronto, there's a really strong group playing leadership role. In fact, some of them are in the audience here, and I don't want to embarrass them, but if you want to wave, any Chime people here? There's one, there are two, yay, three, yay. So just as I'm going to emphasize, this telescope is being built basically by graduate students and postdocs. It is big science, world-leading science, and yet really student-led, trainee-led effort. And it's totally funded by the Canada Foundation for Innovation. And here's just for scale, there's the Chime Fast Radio Burst project team standing in the axis. And this is now, just to give you a feeling for how large this thing is, this is a drone video where you can see, first of all, you might ask, why would you put this near Penticton, British Columbia? The answer is because it's actually surrounded by mountains that act as a natural shield against man-made radio interference, which is ubiquitous now. Everybody has a cell phone. It's a lot of terrestrial interference that's a very big problem for us. And we spend a large fraction of our time just trying to remove man-made signals in order to tease out the fast radio bursts. I just want to point out here, there's a little house under these two dishes here, and there's another one under the other two dishes. There's a whole mess, a huge amount of electronics going on in there that are handling this 13 terabits a second. That's part of our correlator. Now, you might say, well, okay, why cylinders? Why would you build such a crazy geometry? Now, the answer is basically that, conventional radio telescope like Parkes with circular aperture, it can see it's a decent part of the sky, but it's still much smaller than the full sky. And when you have a phenomenon that's transient, where you don't know the next one is, you have to get awfully lucky to have one in your field of view. And they do get lucky occasionally, but in 10, 11 years, they've seen 30. So even though it's 1,000 per sky per day, they don't catch most of them. But with a cylinder, it doesn't focus in one direction. It only focuses in one direction. It doesn't focus the light to a point. It focuses it to a strip. So you get a much larger view of the sky. So if that's the Parkes field of view, now this is the Chime field of view is much, much larger. And so you just have a much greater chance of having one of these transient events in your field of view for you to detect. Now, Chime has no moving parts, so it stares only at what's overhead, but fortunately the sky rotates, because the Earth's rotating, the sky rotates every day. So we cover the full northern sky every single day. And in fact, the telescope was designed not for fast radio bursts, but to do cosmological mapping of neutral hydrogen gas in the distant universe for cosmology purposes. It just so happens it's fantastic for transient science too. And you can see a bit. Stop. Nope. Why won't you advance? There. So this is a sort of a little technical diagram, but you can see the 4 cylinders and all the signals coming into those 2 little huts. That is what we call the F engine, where we have a whole series of field programmable gate arrays built at McGill University for processing those 13 terabits that gets sent to the X engine, which is based on GPUs, if you're into it, it's led out here at a University of Toronto. And then the signal from this portion of this, it's kind of like a supercomputer, 256 computers, is then split, and it can make this map that's used for cosmology. It can also study pulsars, but it's also producing the data set that goes into detecting fast radio bursts. And if you, these little shipping containers on the side here are where the X engine and the fast radio burst electronics sit. The complicated software pipeline in there, and just to show you the inside of one of those shipping containers, contain just massive racks, cooling units, and here are some of the students and postdocs who put all of this together. Really amazing work that these people did. Chime had its first light ceremony in September 2017 with Canadian Federal Minister of Science Kirsty Duncan. She went up right onto the focus and snapped the last few antennas into place to make Chime operate. And here's some pictures of the trainees, the amazing students and postdocs who do so much of the hard work on, in fact, isn't that you, Cherry? Is that you? Yeah, there she is there. And cabling. And now here's how we see the sky. So this is a Chime view of the sky now. Basically, that correlator allows us to see positions, a whole, basically 1,000 independent positions on the sky within that massive strip. It's like having 1,000 Parkes telescopes at the same time. So there's a huge amount of data that we're processing. But what you can see here, this is basically a view of all the different north-south directions within that strip as a function of time. These large strips that you see going totally north-south at one time, that's actually airplanes passing overhead. We could see that with the telescope. These horizontal strips that are fixed in that are basically fixed in north sky position, but that go through as a function of time, that's a galactic radio pulsar that is that's on and is just following the rotation of the Earth. So it's a very bizarre way of looking at the sky, but this is how we see the sky. And I'm very proud to report that just this past July, Chime started seeing fast radio bursts. So this is the first event that we detected. We put out an astronomical telegram. We actually detected it in 2 neighboring positions on the sky because it hit right between the 2 of them. And we've removed the dispersion here, but it was heavily dispersed, and you can see lovely burst. The first time it had been seen at these radio frequencies, by the way. It's the lowest radio frequency these things have been seen at yet. We're very, very excited. Back in January, Nature magazine wrote an article about what to expect in 2018, the biggest science areas coming out. And the very first thing they mentioned, no pressure here, is Chime and fast radio bursts. So it's a very, very exciting time, and we're all working very hard to get this science out fast. But I can't yet tell you what they are, but we are working on it, and I'll just ask you to stay tuned and thank all of the people working on this wonderful experiment, and especially Canada Foundation for Innovation and CIFAR that has played a fantastic role in getting the researchers at these various universities to work together as an amazing Canadian team to bring the science both to Canada and to the world. And I thank you very much for your attention. Stay tuned. There'll be big news from Chime in the coming months. Thank you.
Thank you for that. Make yourself comfortable.
Okay.
It is now my great privilege to introduce Deborah Locke, who is a junior fellow at Massey College. She is a third-year PhD candidate working with Professor Bob Abraham and the Dragonfly Telephoto Array Telescope. Her work includes designing and implementing an instrumental upgrade for the Dragonfly, and she will use this upgrade to study the properties of galaxies and how they interact with the cosmic web. During her time at the University of Toronto, she's also worked with Professor Keith Vanderlyn and HIRAX, which is a South African radio telescope designed to trace large-scale structures in the universe. She holds a combined honors bachelor's degree in physics and astronomy from the University of Victoria. Deborah will ask her own question or questions, and then she will moderate any questions which you're invited to offer to our very distinguished guest. Deborah.
Hi again, Vicki. All right.
Hello.
Thank you so much for the fascinating talk.
Oh, my pleasure.
So I do have a billion questions, but I'll try to keep my part short, and then we'll open up the floor for questions from the audience. fast radio bursts are just fascinating. So you listed a bunch of theories. Do you have a favorite theory for what fast radio bursts could be?
Well, I like to stay as impartial as possible, but there's a lot of hints even in what I've told you today. There's a lot more phenomenology that I didn't have time to go into, but something that brief, something that's so short, it has to be some sort of compact object. It can't be a big, large object that can produce such massive amounts of light in such a short period of time. It has to be compact, and so that pushes you to neutron star, black hole. It seems those are the smallest, densest objects that could potentially produce the sort of energies that we need. Also, to get that kind of energy, likely the emission has to be beamed in a certain way to have it be so narrow, and so beaming compact objects smells to an astrophysicist like there's magnetic fields involved. So among the theories of neutron stars or black holes, a lot of them explain most of the observations, but none of them really explains all of the observations. And so even though, those tend to be the ones that astrophysicists gravitate toward, because there are familiar examples of those phenomena of neutron stars, black holes in the observed universe, I also wouldn't want to rule out something that we really haven't even considered yet, because who knows?
Right. Yeah, I guess one familiar object could be pulsars. So
there are, and I worked on pulsars before turning to FRBs. I worked on pulsars for almost 25 years, and so I'm a big pulsar fan, and yet I wouldn't go to that immediately. I think it's possible, but there's lots of problems with that. There's no pulsar in our galaxy that has produced the amount of energy you need to be seen at a cosmological distance by a terrestrial radio telescope. It's orders of magnitude off. So it's hard to see how it could be a pulsar, but I wouldn't rule that entirely.
So can we detect these fast radio bursts in other wavelengths of light? Have they been just detected in the visible or anything?
Nope.
So far?
So people have tried, but the problem is that optical telescopes that don't usually have the sort of field of view that you need in order to see these kind of flashes. Some have the field of view, but they don't have the fast time resolution. So there are optical telescopes that can see a large area of the sky that look for supernova or something by looking for changes in stars, from one day to another, but not on a millisecond time scale. People have gone with optical telescopes to look at positions of fast radio bursts a few hours to days after the burst was seen, looking for what we call an afterglow. Yeah. That if something exploded there, maybe there's some light trailing off that, and there have been suggestions of afterglows seen in the optical, but absolutely nothing proven, nothing convincing. So people are looking. We have looked at the repeater in X-rays. We did not see any X-rays from the repeater. So no, there are no counterparts yet, but I don't think we've really ruled out their being. It's hard to do that science.
Yeah, okay, that makes sense. So are there other radio telescopes that are also looking for FRBs, like Chime, clearly, as you said?
Yeah, so the thing that's special about Chime is its large field of view, so that if the number of FRBs we can detect per day is large compared to most telescopes. Not most, all telescopes. But other telescopes have gotten there a little sooner, so the ASCAP telescope in Australia, just in a Nature paper today, came out with 20 FRBs. But that's 20 spread over about, I'm not sure exactly how long it took them, but a year or something like that. Whereas we're hoping to see a comparable number, each week or month.
Yeah. So that the data rate of 13 terabytes per second.
Yeah, I had a big B there. It should have been a little b. It's terabits.
Terabits.
That was a mistake on my part, sorry.
Even that seems pretty impossible to store that amount of data.
Yeah, we cannot store it.
So how do you handle that data rate? Do you end up throwing most of that away?
We don't throw it away. It gets processed and added together and combined and analyzed and distilled into forms that are more compact. Mm-hmm. And so for the fast radio burst instrument in that shipping container that I showed you with the guys in this computer racks, that actually ends up getting 140 gigabytes per second. And so it's distilled from 13 terabits per second. It gets down to about 140 gigabytes per second. And then that gets processed in real time to look for fast radio bursts. So that our goal, actually, as we detect these, is to detect them in real time from that data stream and then send out alerts to the astrophysical community, to anybody, public alerts, so that other people with telescopes can know to go look over there, Chime event over there, and then they'll go swing, and maybe they'll be able to detect an optical afterglow. They just need the opportunity, and our goal is to do that. We're not quite there yet, but soon we'll be able to do that.
Right. Okay, just one last question. So the repeater.
Yeah.
Are you guys still watching that one?
Yeah, it is being watched. It's really an amazing source. It's been detected all the way to very high radio frequencies. It hasn't yet been detected at lower radio frequencies, but
at these radio frequencies.
Yeah, we haven't. We're looking. We're still looking, hoping.
Right.
But it's really interesting because it's very unpredictable, and the bursts tend to come in clusters.
Yeah.
So it'll be silent for a long time, it doesn't do anything, and then burst. You'll see, we sometimes seeing like 10 bursts in an hour after not seeing anything for weeks.
Right.
So very hard to predict. The bursts are clearly not random. I always say that with hesitation because then people say not random. But it doesn't mean that it still could be natural. It's just not. It's just they're clustered for some reason.
Yeah, that's so interesting. Okay, before I take over the rest of our time, I wanted to open the floor to get some questions from the rest of you. So there's a couple microphones going around, so I'll just first.
I can't. Can you please repeat? I couldn't hear.
Hello?
Compared to the speed of light, how fast these radio waves travel? And if they come from, let's say, trillions of light years away, is it possible that the source doesn't even exist anymore?
Is it possible that what?
That the source doesn't exist anymore as we talk about it.
Yes. So first of all, the time difference due to the dispersion of light. So the difference in speeds is small. So it's still close to the speed of light. And if you saw the amount of dispersion, for example, the difference in the time for the highest frequency radio wave with Chime to lowest frequency radio wave, it's seconds. So seconds, but out of a light travel time that's billions of light years. So it's a tiny difference, but absolutely the source that created it is billions of light years away. Whether it exists today, we don't know, but we're looking into history because it's taken light a very long time to reach us. So the event happened billions of years ago. We can't know what it's doing today because the light takes that long to travel to us.
So another question maybe from this side? Yeah.
Yes, thanks. Fascinating talk. I have a bit of difficulty understanding what a bright radio source would mean. I sort of, if I could think of it the way you described it, as sort of just intense. Can you maybe make a comparison? What would that look like if it was visible?
If it was
invisible, if it was in the visible part of the spectrum, what would we see when this flash went off?
Right. So let me put it this way. So it's hard to relate the brightness. We could relate it in terms of energy, for example, because a photon comes in with a certain amount of energy. Radio photons are very, very low energy. So if I took the energy in one of these, it's very, very hard to detect in optical, from the same distance. If you put that energy, you wouldn't see it. But some of the fast radio bursts that have been detected are as bright as, or comparably bright to the brightest radio sources in the sky. So we have a crazy unit of measurement called the Jansky. And so something's about, the brightest one, something like 200 Janskys. Now, to relate it to something that is intuitive, if you go up another factor of 10 or so, then it would be a brief flash of static on your analog antenna on your television set. So there are galactic objects that in fact, a pulsar, the Crab pulsar has, we call them giant radio pulses, that if you were looking at your TV when it happened, and now I'm talking about the old style TVs with analog antennas, you would be able to detect that with a television antenna on your TV. So that's about a factor of 10 brighter than the brightest fast radio burst that we've seen. And the range of brightnesses of fast radio bursts that we've seen is fairly large. So they go down by probably a factor of almost 100, fainter than that.
All right. In the back over there, in the middle.
Thank you. I have 3 questions, actually. First, it's actually a significant statement that if the FRB is clustered. So is it only clustered in time, or is it also clustered in space?
You mean the repeater?
Yeah. Oh, no. You are saying the repeater. Okay.
Yeah, the repeater's bursts are clustered in time. And they're all coming from exactly the same position on the sky.
And no other FRB are observed.
Repeating. Yeah, so we keep looking at the other FRB positions, but have not seen any repeats from any other one.
Okay. The second question is how accurate can Chime decide the position of the FRB now? How confident are you for finding the host galaxies for those? Right.
So Chime's the typical region of the typical uncertainty on the sky for Chime will be very similar in general to the error range of the Parkes telescope. So if you remember the biggest circle, so it's not good enough to localize to galaxies. But there's 2 big buts there. One is that Chime sees the same sky every single day. So the Earth rotates, and we get to see the position of every fast radio burst that we detect every single day. And so what my hope is that we will identify many repeaters. So it can't be that the Arecibo event is the only repeater in the universe. That just can't be right. But Chime is very well placed to find other repeaters. And as soon as we start identifying repeaters, then we can go to an interferometer and say there's a repeater there, and they can stare at it and pinpoint it for us, and then we can go and do what you want. The problem is that we can find so many repeaters, we'll need all the time available on the very large array, and all the other rest of the astrophysics community will hate us. And so we can't do that because there's other science to do with interferometers too, and there's only one VLA. So we're going to run into that problem, which is why we have another idea that we really want to pursue. We can make an interferometer of chimes. So if we can make other mini chimes and put them around North America, we can use them as an interferometer. And that is something that we're actively thinking about and hoping to pursue once we get this project fully rolling along.
And the last question is, as the rate of FRB detection increases dramatically with time, what do you expect to do as the first thing to study for the FRB?
Yeah. So there's so many things. So when you have a very large sample of them, so there's one of the interesting questions is, are they uniformly distributed on the sky? So if they're cosmological, they should be fully uniform on the sky. And from the 30 known so far, they seem to be uniformly distributed on the sky, except that they seem to avoid the plane of our galaxy. And so cosmological population should not know anything about our galaxy, but there's material in the galactic plane, there's extra free electrons there, that could cause, there's some suggestions that might hinder the ability to detect them, and there's good reasons for that. So we can test that sort of thing. And you might expect to see overdensities of fast radio bursts in certain regions of the sky because galaxies like to cluster, and so if FRBs come from galaxies, eventually you should start to see the imprint of what we call large-scale structure on the distribution of FRBs in the sky. So when you have a large sample, you can do that, but you can do other things. You can look at the distribution of dispersion measures. You can look at the distribution of widths. You can look and see, is there a brightness dispersion measure correlation? So I could go on and on about what we can do with, even without localizing Chime events, there's tons of science that will give us clues to, they might not give us the final answer, but they're going to get us further towards solving the problem. Thanks.
CIFAR, I always get to ask the dumb question. So here's my dumb question, Vicki. It has to do with the origin, the material origin of a FRB or FRBs. So implicit in the question of where do they come from, are you assuming they all come from the same kind of source?
Yeah, that's a great question. So
I think I asked you that at Whistler, actually.
Oh, maybe.
But you said, I don't know, but I'm going to ask you again, because this is now a year later, so you should have the answer.
Yeah, we don't have the answer yet. No, we'd love to know that. And already, when you have one that repeats, and the others don't seem to repeat, that suggests right there that there's different phenomena, that we've basically opened the sky looked at it in a different way because computers are so fast and because we have this technology that allows us to see the fast transient universe. There's many different types of objects that can produce radio bursts. And, in the 70s, 80s, and 90s, there was a different problem called the gamma ray burst problem, and some of you might have heard of that, where there were bursts of gamma rays going off around the sky, and that has been studied and solved largely, and did turn out to be 3 different classes of gamma ray bursters. So there's no reason to think that there can't be different classes of fast radio bursts among the sources that we've already detected.
What an amazing talk, an amazing discussion. I want to invite all of us to thank Vicki and Deb for just a fabulous piece of talk. Now you know why I have the best job in science on the planet, actually. I have 400 Vicki Kaspis to deal with. So I want a special thank you to you, Vicki, for coming this way, and a special thanks to you, Deb, for great questions, really great questions. I also would like to have a special thank you to Principal Siegel. Shortly after he became principal, Rebecca Finley and I came to see Hugh and asked him if he would be interested in having some kind of series like this. And I think it's to his great credit that he immediately agreed, and I think it reflected his openness, his understanding of the importance of science, and the understanding of science to society. And here we are with our 4th great lecture series. And I'm going on about Hugh because he announced a while back now that he'll be stepping down as the principal of Massey College sometime after this summer, or at some point after, I think, a truly remarkable 5-year term as principal of Massey College. And I want to take this opportunity publicly, Hugh, to thank you for your generosity of spirit, the partnership that we've had, the recognition of the importance of science to the world, especially in this troubled time when science and evidence are being tossed into a sort of a maelstrom of partisanship and ideology. And so your vision has been really terrific, and you've been a great partner to work with. Hugh has had, I'm sure we all know this, but has had a truly distinguished career as principal secretary to Prime Minister Mulroney, and I'm probably going to leave out some things. He was a senator, a distinguished senator, and now he's been principal of Massey College, and he's what Canada needs a lot more of, which is a public intellectual. I feel really privileged to have worked with you, both in my job as president of CIFAR and as a senior fellow at Massey, and I wish you really the best as you go on from Massey College. Thank you very much.